On August 6, 1945, the United States dropped an atomic bomb on the Japanese city of Hiroshima. The bomb was known as Little Boy. 3 days after the Hiroshima blast, the United States dropped the second atomic bomb on the Japanese city of Nagasaki. The bomb was code-named as Fatman. Fatman is more efficient than Little Boy. The Hiroshima bomb Little Boy consists of 64 kilograms of enriched uranium to produce 15 kiloton blast. By comparison, Nagasaki bomb, the Fat Man consists of only 6.4 kilograms of plutonium to produce 21 kiloton of blast. Meaning that Fat Man is more efficient than Little Boy. Fat Man was built by the scientists and engineers in the Los Alamos laboratory at the Manhattan Project. During the Manhattan Project, Robert Oppenheimer was the director of the Los Alamos laboratory. He is often known as the father of the atomic bomb. The bomb was 128 inches long and 60 inches in diameter. It weighed approximately 10,300 pounds. Here's the size of a person in comparison. Let's take a closer look inside the Fat Man. Fat Man was powered by a plutonium sphere. The plutonium sphere is similar to the size of a soccer ball. The sphere weighs only 6.4 kilograms. This is responsible for the tremendous explosion. Plutonium is a radioactive metallic element. It was discovered in 1940. Plutonium is considered as a man-made element. Trace elements of plutonium are found in naturally occurring uranium ores. The plutonium sphere is surrounded by explosives. These are the explosives lenses. It is a highly specialized shaped charge. It is composed of 60% of RDX and 40% of TNT. The bomb is equipped with 32 bridge wire detonators, which fitted around the explosive lenses. 24-volt batteries are mounted on one side of the bomb, which is connected to the fusing system. On the early morning of 9 August 1945, the Boeing B-29 Superfortress takes off from Tinian with Fat Man. The bomber's primary target was the city of Kokura. After 7 hours of flight, the aircraft arrived over the target. Due to thick clouds and drifting smoke, they could not able to drop the bomb on Kokura. So, they shifted their target to Nagasaki. Nagasaki was a port city located about 100 miles from Kokura. It was larger, with an approximate population of 263,000 people. At an altitude of about 17,000 feet, the Fat Man was dropped over the city of Nagasaki. 47 seconds later, the Fat Man reached an altitude of about 1,600 feet. The Archie radar antenna emitting and reflecting the signal to the ground. These signals are used to detect the detonation altitude. The radar altimeters were used to reliably detect final altitude. When the altimeters sense the correct height, then the 32 exploding bridge wire detonators, simultaneously releasing electrical sparks. Due to this electrical spark, all of the explosives would go off simultaneously. The thick layer of the metal casing helps to create an implosion shock wave inside the casing. The medium-density aluminum pusher transfers the imploding shock wave. The shock wave then compresses the inner components, passing through a boron plastic shell. Then the shock wave transfers to a natural uranium tamper, and the sphere of plutonium would be compressed. In the middle of plutonium, two elements are called polonium and beryllium. Due to the compression, the two metals mix them together, and thereby releasing a burst of neutrons. Approximately 10 milliseconds later, the nuclear chain reaction occurs. One atom of plutonium is hit by a neutron. It splits into two, releasing energy, and it produces two neutrons, each of which goes on to react or split other atoms of plutonium. The Fat Man exploded at an altitude of about 1,600 feet. If it exploded on the ground, the result of the explosion will be relatively low. The bomb detonated with the same force of 21 kilotons of TNT. Approximately 40,000 people were killed and destroyed nearly every building within 3 square miles of the epicenter. Inside the epicenter, the thermal heat from the explosion vaporized some people instantly. The damage came from three main effects: blast, fire, and radiation. The blast from a nuclear bomb is the result of an X-ray heated air, called fireball. The fireball was an extremely hot and highly luminous spherical mass of air and gases. The firestorm affected area was roughly 3.2 kilometers from the epicenter. As a result of the explosion, it's releasing radiation into the air. The alpha radiation will not do much harm. These particles of ionizing radiation can block by wearing well-protected clothing. Beta radiation is a little more serious. Beta particles are capable of penetrating the skin and causing radiation damage, such as skin burns. Gamma radiation is more dangerous than others. It has so much penetrating power. Gamma rays can pass completely through the human body. It can also result in long-term health effects, such as cancer, cardiovascular disease, and gene mutation. It causes
Getting your innovations to market quicker makes a difference in the world. We're here to help make your job faster and easier. We collaborate with you by drawing from your decades of history in manufacturing, process development, and material science. And then we pair that with significant filtration know-how and biopharma experience. You can count on us for clarification and purification solutions that reinvent and optimize processes, while improving purity, increasing yield, and saving time. We're ready to make a difference alongside you. Our bioprocessing application specialists work bench to bench with you to realize your goals. We can help you improve process efficiency, reduce impurities, and solve your complex challenges as they arise. Let's partner on advanced solutions for purification, filtration, and clarification. We never stop solving for you.
And to bring you this story, we interrupt our program.
An American airplane dropped one bomb on Hiroshima.
The White House has just made an important announcement on the war.
Buzzing with the news of the atomic bomb. The world would not see the plan. We have now added a new and revolutionary increase in destruction.
Aren't sure yet what hit the place.
On August 6, 1945, at 8:15 in the morning, the United States dropped an atomic bomb on the Japanese city of Hiroshima. As modeled here, the atomic bomb, codenamed Little Boy, was the first nuclear weapon dropped on humans. It was an attack during World War II, and there was no warning given. Carried by a B-29 warplane, the bomb was dropped from about 31,000 feet and fell in 43 seconds. It exploded about 1,900 feet off the ground. Inside the bomb, a controlled explosion created with high explosives propelled a subcritical mass of uranium-235 down a long tube, similar to the barrel of a gun, where it collided with a second subcritical mass of uranium-235. The collision triggered a nuclear fission chain reaction, which detonated the bomb. It detonated with the same force as 15,000 tons of TNT, forming a mushroom cloud about 60,000 feet tall and releasing radiation into the air. The explosion resulted in a flash of blinding light, followed by intense heat, killing an estimated 80,000 people instantly and destroying nearly every building within 1 mile of the epicenter. Fires caused by the explosion's intense heat lasted for days, destroying more than a 4 square mile area from the epicenter. Over 50% of the people that were killed died of burns. Many of those that weren't killed by the flash burn, blast, or fire died of radiation poisoning. Others were trapped in rubble, and thousands were injured. The health effects, including cancer and birth defects, have been felt for generations. Three days later, another atomic bomb, made with plutonium, was dropped on Nagasaki, killing at least 74,000 people. A nuclear weapon has not been used on a civilian target since.
The Japanese have seen what our atomic bomb can do.
Almost beyond the comprehension of mere human.
I realize the tragic significance of the atomic bomb.
And even now, after hearing many times the description of this new weapon, its capabilities continue to tempt human imagination.
Vladimir Putin strode into town.
Почему раньше здесь не было людей, которые способны были принимать решения? Почему здесь-то забегали все как тараканы перед самым моим приездом?
Unlike Medvedev, Putin confronted the factory owners.
Считаю, что вы сделали заложниками своих амбиций, непрофессионализма, а может быть просто экстремальной жадности. Тысячи людей. Это абсолютно недопустимо. Если собственники договориться между собой не смогут, то единый комплекс все равно будет восстановлен. В том или другом виде, то это будет сделано без вас.
He demanded the owners, including billionaire Oleg Deripaska, sign an undertaking to restart the factories.
Вы посоветуете договор, да? Аль Борис подписал? Я не вижу вас тут. Сидите, пишите. Идите.
Classic Putin. But if a country as big as Russia needed a personal visit from the boss to get one factory back to work, then it was in serious trouble.
There are different bunker buster bombs of different calibers, but what sets it apart from the rest is this GBU-57, which is typically delivered by the B-2 Spirit stealth bomb. Due to the bomb's large size and weight, the aircraft can carry only 2 of these weapons in its bomb bay compartments. While it lacks thrusters, the weapon is equipped with 4 active lattice fins and a precision guidance system that enables it to glide accurately to its target using military-grade GPS. Constructed from a specially designed high-performance steel alloy, using its weight and falling in gravity to penetrate and dig itself up to 200 feet of underground soil or concrete. We'll also look into the difference between the massive ordnance penetrator and the mother of all bombs and step-by-step process and how they work, following the video ahead. To give you an idea of the varying levels of penetration capability among different bunker buster bombs, let's compare a few examples. First, we have the BLU-109, also pronounced blue. It is a 2,000-pound bomb developed in the 1970s. This weapon is capable of penetrating approximately 1.8 meters or about 5 feet of reinforced concrete. Next, we move on to the GBU-28, which is equipped with a laser-guided system in its front. This bomb can penetrate to a depth of nearly 6 meters, equivalent to roughly 20 feet, which is as tall as a 2-story building. However, neither of these compares to the massive capabilities of the GBU-57, also known as the Massive Ordnance Penetrator. It can penetrate over 60 meters into the ground, around 200 feet. To put that into perspective, this depth is comparable to the height of 20-story buildings, depending on the floor heights. These examples demonstrate the significant advancements and differences in penetration levels among these specialized weapons. Let's put an average human here against this weapon, which is 20.5 feet long, giving it a streamlined aerodynamic shape that is crucial for stability and precision. With a diameter of 31.5 inches and weighing an incredible 30,000 pounds, translating to approximately 14,000 kilograms, it utilizes its massive weight to generate the kinetic energy required for deep penetration. This heavy, compact design enables it to break through over 200 feet of reinforced concrete, making it one of the most effective bunker-busting munitions in the world. Let's take a look at the parts of this weapon. The most important part is the body casing, made of hardened ferrocobalt alloy to withstand impact. Interestingly, the body comprises more than 80% of the bomb's total weight. Inside this cover, you will find the following components. At the front is the nose fuse well, all of which are joined by a fuse conduit. Sandwiched within this rod is the explosive-filled 5,000-pound warhead, which translates to approximately 2,267 kilograms. This conduit then connects to a tail fuse, which, interestingly, is the main detonator and is crucial for delayed action. Moving to the back, nestled inside the tail, we discover the intricacies of its guidance system. Here, the inertial guidance kit collaborates seamlessly with the military-grade global positioning unit, ensuring precise navigation towards its intended target. Alongside these components, one can find the adapter ring, which facilitates the attachment of the telemetry antenna, crucial for transmitting data, as well as the encryption key battery, which safeguards sensitive information. Venturing deeper into its structure, we encounter the kernel batteries vital for powering the system, and the composite fins strategically positioned to aid in directing the missile towards its objective. These fins, meticulously controlled by internal gears, maneuver with precision, responding to commands to adjust the trajectory accurately. Let's take a look at the smaller bunker buster and how it works. It has a laser sensor at the front, and just behind that are adjustable fins. In the midsection, there is a warhead that weighs approximately 650 pounds, containing tritium explosive. This is a mixture of 80% TNT and 20% aluminum powder. Finally, we have a retractable fin at the rear. To give you a better sense of its size, comparing it to a person can be helpful. The casing has a length of approximately 19 feet long, which translates to around 5 meters. This section is made of an artillery barrel, which is very strong, and has a diameter of 14.5 inches, which translates to around 37 centimeters, making it relatively narrow. They intentionally made the smaller cross-sectional area. This means the bomb displaces less material, whether earth or concrete, as it penetrates layers of reinforced bunkers or buildings. The smaller cross-section allows it to enter deep into buildings, potentially avoiding steel and concrete. Let's move back to the MOP and its cost factor. The development cost of the GBU-57 is estimated to be between $400 and $500 million, with its production price per unit around $3.5 million. Meanwhile, the GBU-28, a 4,000-pound bomb, costs approximately $100,000 to $150,000 per unit. While the per unit cost of the BLU-109 is approximately $25,000 to $84,000 for each JDAM kit. Let's take a look at how this works. Step 1. The bomb deployment platform, as previously mentioned, a B-2 stealth bomber flies at a very high altitude. When the aircraft reaches the designated location and the conditions are optimal, it releases the weapon. The bomb is designed for precision, and the deployment height plays a crucial role in its trajectory and effectiveness. Then step 2 comes to targeting precision. The bomb is outfitted with advanced guidance technology, including GPS and inertial navigation systems, which are military-grade satellites. Then comes step 3, that is adjusting the trajectory. The guidance information and data is then transmitted to the bomb's 4-lattice motor's fin located at the rear. These fins can move and adjust in real time, allowing the bomb to correct its course as it descends under the force of gravity. These adjustments are essential because the weapon does not have thrusters to change its trajectory. Instead, it relies on the movement of these fins and high-altitude drop to control its flight path. This is why the bomb must be deployed from a very high altitude so it has enough time and distance to adjust its trajectory accurately. Here comes the most difficult part, that is step 4, impact and penetration. The bomb, known as the Massive Ordnance Penetrator, weighs approximately 30,000 pounds, which is around 4,000 kilograms. When it reaches its target, it strikes with immense force designed to penetrate deep into hardened structures, such as bunkers. The energy upon impact allows the bomb to bury itself over 200 feet into reinforced concrete, ensuring it delivers its payload precisely where it is intended for maximum effect. Finally, Step 5 involves the tricky part of arming the weapon. It was installed with 2 SDB fuses. Double fuses are required as a backup. The first is for G-sensing and the second is the time delay fuse. Why the redesign was necessary was to ensure that the bomb could strike facilities buried beneath significant layers of hardened material. For this reason, the fuses are placed at the rear of the bomb to prevent them from being damaged. Once the time delay or the G-sensing fuse reaches its destination, it can blow up, creating a mini earthquake that can bury bunkers and 20-story buildings inside them. Many people often confuse the Massive Ordnance Penetrator MOP with the mother of all bombs, MOAB, which stands for Massive Ordnance Air Blast. The mother of all bombs weighs approximately 21,600 pounds and is designed to detonate above the ground, creating a massive shockwave and blast radius. However, unlike the MOP, it does not have penetration capabilities. This MOP is capable of digging up to 200 feet underground before exploding. While the Massive Ordnance Penetrator can be deployed from bombers such as the B-2 Spirit aircraft. But this is not the case with the mother of all bombs, is so large that it must be delivered via a C-130 aircraft using a pallet system. Once deployed, the bomb is dragged by a parachute and falls under gravity, guided by an inertial navigational system and military-grade GPS. On April 13, the U.S. dropped one of its largest non-nuclear bombs on a tunnel complex in eastern Afghanistan. When it detonated, the blast sucked all the oxygen from the caves. We make original videos from scratch, so please do subscribe and hit the notification bell for more videos.
Okay, so I'm going to talk to you now about plutonium. So I've obviously put two uranium is the booby man periodic table, but if uranium is the booby man, then there is a Hannibal Lecter at the periodic table, and it's a couple of places to the right, and that element is plutonium. Plutonium has a really quite nasty reputation. For example, there's a book here, Plutonium, History of the World's Most Dangerous Element. When the human race evolved, it evolved with uranium in the environment, so we physiologically can actually deal with it to some extent. Plutonium is a man-made element. It wasn't there in the environment when we evolved, and this means we've got essentially zero tolerance to it, so that makes it quite dangerous for us. We're at Sellafield in the northwest of England, we're at the NNL Central Laboratory. We're interested in plutonium because we need to be able to recover it from spent radiated nuclear fuels. You can't just use plutonium in a regular laboratory. You have to have a laboratory which is specifically designed to handle it, so it's handled safely. It's at the point in the periodic table where it does interesting things. There are not many elements which you can say when they were created. You can sometimes say it was discovered in 1869 or 19 whatever, but plutonium was made for the first time in 1914. The reason that it was made is that it's a radioactive element and it decays away with a
half-life that depends on which particular isotope it is. If plutonium was created at some time during the formation of the solar system, it has all decayed away long before scientists ever started looking for it on Earth.
I have seen a lump of plutonium once. I don't think I could tell you where I actually saw it, but it does just look like a shiny piece of metal, what we'll see today as plutonium in solution. And that's really interesting because plutonium's got some really intense colours, and the colours change depending on the oxidation state of the plutonium as well. It's incredibly dense as a metal. You could take it with a hacksaw and the hacksaw blade would break before you chipped any plutonium off. The sheer density is shown by the fact that a golf ball sized lump of plutonium would be over a kilogram easily, really quite heavy stuff.
So here, the intention is to recover the plutonium from spent nuclear fuel. Plutonium is present in about 1%. What we do is use solvent extraction in order to remove the plutonium from the fission product in the aqueous phase and move the plutonium up into a solvent phase. And that solvent phase is a mixture of tributyl phosphate and a diluent called odorless kerosene. Here we have some plutonium nitrate, and this plutonium is in oxidation state 4, and that's the oxidation state that's extractable into tributyl phosphate. I've got two separate solutions here. They're both plutonium nitrate, but just at different concentrations. It is dangerous for several different reasons. It is dangerous because it is the basis of atomic bomb. The second atomic bomb, so-called Satman, that was dropped on Nagasaki in 1945, contained plutonium, and it was the plutonium that made it explode. It was a bigger bomb in terms of the size of explosion than the first bomb that was dropped on Hiroshima. But it's also dangerous, plutonium, because it is very poisonous. Many heavy metals are poisonous, particularly, say, thallium. But plutonium is poisonous not just because of its chemistry, but because of its radioactivity. Plutonium decays radioactively by emitting alpha particles, helium nucleus, and when that hits the cells of your body, it can cause terrific damage, and that can lead to cancer and so on. I'm going to take some 30% TBP, so this is the solvent phase. You can see there, it hasn't been mixed yet, but the solvent is less dense than the aqueous phase and resides on top of the aqueous. But you'll see in a minute that that brown colour will go up into the top phase. According to this book, there is a club, or there was a club, in Los Alamos, the bomb factory where they developed the chemistry of plutonium and made the plutonium bomb, of 4 people, which have rather a strange name. This says UPPU, which means your urine contains plutonium. And these are people who, through some sort of accident, had plutonium in their body. There was one person that was described called Margot, who was working with a glove box, just like the ones that we saw in the MNL lab. And he had, for some reason, a needle, and he stuck the needle through the finger of one of his gloves. And he pulled out his hand and saw that there was a tiny black speck in his hand, which was a fragment of plutonium. And although the doctors tried to dig this out, for the next 50 years, plutonium could be detected in his urine. And it wasn't very high concentration. According to this, he had to provide a gallon of urine, that's 4 liters, before they could detect the plutonium, but nevertheless, he survived. Okay, so I've got 2 samples there with plutonium nitrate at the bottom and tributyl phosphate of this protein on the top. So what I'm going to do now is put them into this device, which is called a vortex mixer. So while that's That's mixing. Plutonium's going up into the solvent phase. It'll form an emulsion, and the solvent will then start to disengage from the aqueous phase, and the two phases will separate out.
Plutonium is formed in the nuclear fuel of nuclear reactors. Uranium, which has atomic number 92, can be transformed into plutonium, which has atomic number 94, by absorption of neutrons. So the uranium absorbs neutrons. That is the uranium-238, the sort of uranium that does not spontaneously fission and provide the energy for nuclear reactor.
The Hanford, Washington Active Material Production Plant, where uranium-238, the most abundant isotope in natural uranium, is converted into a completely new fissionable element known as plutonium-239.
So it's the so-called, if you like, inactive uranium isotope, but that can absorb neutrons and be transformed into plutonium.
Okay, that should be done now. Looks like an emulsion at the moment. As it separates, you'll see that the top phase has now got the colour in it. The plutonium nitrate has now formed a chemical complex with PDP molecules. And those PDP molecules have made the plutonium soluble in the organic phase. In processing of irradiated nuclear fuel, all the fission products would now be in this bottom phase. And the plutonium and uranium would be in this top phase here. So you've separated them out.
Plutonium itself, the metal, is actually a very fascinating material. I've never seen it, but it's meant to be a very hard metal, but it has a surprisingly large number of allotropes. An allotrope is a different crystal structure. Plutonium has 6 or 7 different allotropes which differ in their hardness, their mechanical properties, even their density. This makes the machining of plutonium, which is necessary to manufacture nuclear bombs, extremely difficult. It also has quite a low melting point. It melts at 639 degrees centigrade, which is really very low melting point for a heavy metal. For example, osmium, which is not far away in the periodic table, has a melting point well above 3000 degrees centigrade. Some of these isotopes of plutonium are so radioactive that they're really quite hot. So if you feel the sample, some of them can even be glowing red hot, but even the less radioactive ones apparently feel quite warm to touch. So you have to be quite brave to touch them.
What happens in a solvent extraction process is that the solvent is separated from the aqueous phase, and then new aqueous liquor is added to that solvent to try and recover the plutonium from it. What we're going to do is remove the aqueous liquor from this now, from the bottom, and replace it with some fresh liquor that's got a chemical within it that will promote recovery of the plutonium from the solvent. I'm taking the aqueous phase out from the bottom. Of course, on an industrial scale, this is done with a variety of devices.
Why are you trying to get the plutonium outside? Because it has to be disposed of in a special way, or because you want to reuse it?
It's separated into a pure form so that it can be reused in things like MOX fuel, which stands for mixed oxide fuel. So that's where you combine plutonium with uranium, and you can put it back into nuclear reactors and generate new energy.
There is also an interesting feature that when they decay radioactively, they give off these nuclear helium atoms. So as you get an older and older sample of plutonium, the helium builds up in this crystal structure. So although it looks like a piece of metal, in fact it has helium atoms inside it, rather like the food inside the cake. And because of this crystal structure, you tend to have crystallites with boundaries, so-called grain boundaries between the crystallites, and the helium can accumulate on the grain boundaries and weaken the metal quite substantially. The helium has two problems. Obviously, in the short term, if you are somebody who makes bombs, you have to be careful that you don't build up too much helium in the core of your bomb, because it then may not perform properly.
Here in sequence are the four snapper blasts. Detonated atop their steel towers on the 7th and 25th of May and the 1st and 5th of June.
The second problem is that if you are storing plutonium, which has come from reprocessed nuclear fuel, and is just being stored at waste until it's safe to be in the environment, you will bury it somewhere in the ground in a very strong container. And when you're designing that container, you have to allow for the fact that your metal will start producing a gas as it decays, and therefore your container has to be able to withstand the internal pressure so it doesn't suddenly explode, which would be embarrassing, if not for you, for your grandchildren or their grandchildren when they suddenly discover that these secure containers have blown up.
Did you just describe the explosion of a container containing radioactive plutonium waste as embarrassing?
Yes.
How do it work? For all the excitement about plutonium, it all looks pretty harmless there, that muddy brown solution.
Well, it's highly radiotoxic, and you wouldn't want to drink that either.
Well, I won't know. Even that looks a little bit like Coke.
In order to get that plutonium back into the aqueous phase, I'm going to use two different techniques. One is a reduction to get plutonium-4 into plutonium-3 oxidation state. So what I'm going to do to this one is add a chemical called hydroxylamine nitrate. This is another method for using a complexant, which means that it forms a chemical molecular compound, and the chemical that we're using is called acetyl hydroxylic acid. When we've mixed it, all the plutonium will be in the bottom. Okay, so this is the acetyl hydroxylic acid solution, and it's just disengaging between the aqueous and the organic phase. And as you can see, the colour in the top phase is completely gone now. So that's the solvent. Solvent is now free of plutonium, and it's come back into the aqueous phase. And that aqueous phase can then be sent to downstream plants for final purification and conversion into the final form, which is plutonium dioxide. So this hasn't been quite as effective, but you can see there the orange colour that was in the top half has been diluted now, and most of the plutonium is in the bottom half as plutonium-3.
So I have another story. I've told it before, but it's really good, and Brady wants to hear it again. One of the people who taught a professor at Cambridge, Alfie Maddock, worked on plutonium during the Second World War. And one night, when he was really quite tired, he spilt the entire United Kingdom supply of plutonium, which was 10 milligrams, onto the table, the bench that he was working on. He was really upset. He'd lost the whole country's supply. So he just saw at 9.5 milligrams of the 10 milligrams he'd lost. And he would have hidden the whole thing, but he was so tired by then that he didn't have the energy to repair the tabletop. So when people came in the next morning, there was a big hole and aluminum nitrate.
also very useful for me, the reader's reaction. It basically predicts what the audience may think when they read it. Their key takeaways, possible questions, even where they get confused. So go ahead and level up your productivity and get Grammarly today.